This is this topic. I would like to talk about the application of gold nanoparticles for medical diagnostic purpose. So I just review the gold nanoparticles for detection of some infectious diseases, uh, and then summarize here in the presentation. So let's look at the overview of this applications of gold nanoparticle. So first of all, I would like to introduce the gold nanoparticles and the infectious disease for like background knowledge, and then we go deeper in detail about the synthesis of the gold nanoparticles, and then the detection methods, including precipitation, the strip taste, and many other kinds of methods that I would like to show you here. So first of all, there are so many kind of infectious diseases. So there are kind of disease that is infected by some kind of virus or bacteria, thing like that. A very famous example is a leptospirosis. Here in Thailand and the tropical region, it is infected uh, spirochete bacteria. Leptospira interrogans actually for the name of this kind of species. So after infected, our body will have kind of raising up our body temperature, trying to kill the bacteria, things like that. So actually this is not very dangerous bacteria compared with coronaviruses and uh, influenza, things like that. But anyway, it causes health problems. So if you want to kind of get it off or control this leptospirosis, we have to then analyze or diagnose the patients who were infected with this kind of bacteria. So one of the thing that or one of the tools that we can use is the gold nanoparticles or AuNPS. The gold nanoparticles has this kind of specific or characteristic color due to its surface plasmon resonance. It is actually the bouncing of electron clouds on the surface of the gold nanoparticles, which is can be stimulus by or activated by the electronic field of electromagnetic radiation or by the light. So if the wavelength or if the frequency of the electronic field is resonate with the electron clouds bouncing on the gold nanoparticles, so then our gold nanoparticles can absorb that kind of wavelength, and as a result we can see the gold nanoparticle colloidal solution in a characteristic colors like red colors, for example, and it is described by an equation proposed by Mies, so we call this equation as Mies theory. The synthesis of the gold nanoparticle is quite simple. So this kind of nanoparticle is very famous and can be applied in so many fields due to its easy to operate, its stability, and yes, the synthesis method of the nanoparticles here is very simple. There are actually many kind of methods, but the one that I want to show is the very simple one, citrate reduction method or the chemical reduction method using sodium citrate as a reducing agent, and also the sodium citrate can act as a stabilizer who can then cover the surface of the gold nanoparticles, preventing them from aggregation. So starting from tetachloroauric acid, or maybe we can start from tetachloroaurate ion, like sodium salt or potassium salt, thing like that. Then this gold 3 plus can then reduce down to gold 0, and by the metallic bonding they just aggregated, forming a nanoparticle, metallic nanoparticles at the very end. This method was firstly developed by Triplex in 1963, and still we can use it since then to nowadays. As you can see on the left hand, it is the clear yellow color of the tetrachloroauric acid, and on the right hand it is the characteristic red color of the colloidal solution of gold nanoparticles. So as you can see, the colloid gold here is quite clear to our naked eyes because the gold nanoparticles here inside is very small. So we can simply check the colloidal properties by the Tyndall effect. So if we use like laser pointer, as you can see, the laser can pass through the yellow solution nicely without anything, right? But for the red colloidal solution, we can see the Tyndall effect. We can see the beam of the red laser here in the colloidal gold. So this indicates the formation of the nanoparticles. And yet we can also characterize the gold nanoparticles here by SEM image or TEM image. This is a TEM image of the colloidal gold synthesized from previous picture. And zoom into the picture a bit, we can see that our gold nanoparticle is about 9 nanometer, 9 to 10 nanometer. It depends on the concentration of the citrate ion of the gold gold, and also depend on the solvent and everything, temperature. So as you can see here, the absorption band from UV visible spectroscopy, we can see the absorption maximum about 500 something, and this due to the surface plasmon resonance. So as I said, the light with the wavelength about 520, this electronic field can resonate with the electron clouds on gold nanoparticles with these shape and size. So it's our gold or our electron clouds absorbed these lights, and because this 520, which is slightly green color, so our eyes can then detect the rest of the wavelength and combine them together in red color. So we can see the red color out of the gold nanoparticles colloidal solution here. The mechanism of formation of the gold is starting from the gold 3 plus up there, right? And then we have the reduction by sodium citrate, or we can use any other kind of reducing agent as well. And then the gold 3 plus can be reduced down to gold 0. So gold zeros can then attach with themselves, okay, and forming bigger cluster of the metallic gold. And at the end, we have the first stable nucleus of the nanoparticles, as you can see here in the picture out here. So it composed of 13 atoms of gold, because it is actually the hexagonal closest packing, or maybe cubic closest packing ABC system. Another method of this reduction, maybe after the first atom was reduced, the gold ion absorbed onto this atom, and they reduced down again by the citrate, and at the end we have two atoms, right, and absorbed new ions of the gold 3 plus, and then the mechanism continued, and at the end we have this stable nucleus of the gold, and it is irreversible. So after we have this kind of cluster, they can then aggregate it, forming a bigger cluster of the gold. So at the very end we have nanoparticles in our controlled environment. If we not control the formation of the gold nicely, then they can end up as a chunk of bulky gold, uh, solid gold. So to prevent the over aggregation, we have to stabilize our gold nanoparticles using. We can use two mechanisms. The first mechanism on the upper picture is cover the gold nanoparticles with the polymers or any kind of long chain steric effect. Then we have steric hindrance and preventing the gold from aggregation. Another kind of method is using the electrostatic repulsive force. So in this case of the citrate, normally the excess amount of sodium citrate can absorb on the surface of the gold nanoparticles. So now the surface of the gold is covered by the anion of citrate. So anion negative charge, we can have then the electronic repulsive force, preventing them from aggregation. So the gold nanoparticles can re-aggregate it when the environment of the solution was disturbed by any kind of thing. Actually, there are many kind of factors that can induce the aggregation of the gold. So in this case, we're starting from the gold, colloidal gold, and then we add the NSS or normal saline solution, the sodium chloride solution at 0.9%. With increasing amount of the NSS or sodium chloride ion, so with increasing the ionic strength in our solution. So after the ionic strength is increasing, then the solubility of the citrate changed. So the absorption of the citrate ion onto the surface of the gold nanoparticle is changed. So by this kind of changing, what we can see is that the gold starting to aggregate it, the nanoparticles starting to aggregate it together, increasing up the size of the nanoparticles into micrometer scale and so on. So what we can see is the absorption band, the surface plasmon resonance absorption band at 520 is decreasing down. But then on about 600 something, the absorption here is increasing up. But actually this is not as the absorption peak. This is the scattering peak due to the size of the particles is increasing, and then after the size is big enough, then they can scatter the beam of light. So what you can see here is a scattering mode on the right hand, and because this is about 600 something that is the light was scattered, so at the end we can see that our colloidal solution is changed the color from red of the absorption at 520 to be kind of bluish color, but because of the scattering at about 600 something nanometer here. So we can starting to use it for kind of diagnose or kind of sensor. The first kind of work on the application of sensor for gold nanoparticles that been done here in my group actually is the urine pregnancy test, comparing with the commercial test kit. So as you can see that the right hand side, which is a positive pregnancy urine, so that means this urine is obtained from a pregnant woman. So from gold nanoparticles or colloidal solution, we just drop the urine here inside, but as you can see the color is still in red color. But for the negative, that means the urine here is from normal women. So after we dropped it down mixed with the gold nanoparticle colloidal solution, the solution is changed from red to be blue color like this. So this is because of the kind of ionic ions, sodium chloride and things like that in the urine. So it induces the aggregation of the gold. But for pregnancy women, they have something to prevent the aggregation of the gold nanoparticle. So we can use the gold nanoparticle colloidal solution to simply detect the pregnant women from the urine. So as you can see, this is comparing with the test kit, commercial test kit. So this is positive test kit. So we have red color of the urine mixed with the gold nanoparticles. But for the negative test kit here, is this turn blue. So what happened? This is because in the pregnant women urine, we have human chorionic gonadotropin, which is a kind of proteins secreted from pregnant women. So this kind of protein is quite huge actually. It's about 8 nanometer. So this protein can absorb on the gold nanoparticles and preventing them from aggregation, even though we have very high ionic strength in the urine. And this is a TEM image of the gold nanoparticles together with the pregnant women urine, HCG rich urine actually. So as you can see that the gold nanoparticle is now surrounded by kind of foggy things, right? And this is actually the proteins, the HCG proteins. So zoom into the picture a bit. As you can see, these are the proteins, right? So it is stabilized by the proteins. So not only the HCG hormones that can stabilize the gold nanoparticle from aggregation, there are many proteins tested to see whether they can prevent the aggregation of the gold nanoparticle or not. So in this study, they used BSC, bovine serum albumin, HCG, and gelatin. So with proteins and NSS solution, so what we can see is that so with the protein mix in the gold nanoparticle, all of the gold nanoparticle colloidal solution still in the red color. But then we add 0.9% sodium chloride into the mixture. What we can see is the G and H, which is corresponding to the HCG and gelatin, the gold still in red color. But BSC or bovine serum albumin and the control one turned already into blue color. That means some kind of proteins with some concentration, with a specific concentration, can prevent the gold nanoparticles from aggregation. It's due to the affinity of the proteins onto the surface of the gold nanoparticles, which actually depends on the structure of the proteins and also from the charge of the proteins, because proteins can compose of many kind of amino acid, right? So it depends on the charge of the proteins as well. But that is not very specific. We can also use it as very specific binding to selectively or specifically detect something. The specific binding can be found in antigen antibody system or in DNA PNA system or DNA RNA system, thing like that. So we can constructing kind of specific binding of the gold nanoparticles to the target using antigen antibody chemistry. So first example here on the right hand, we're starting from a kind of solid support and then attach the IgG onto the surface. The solid support used here is the activated glass slide. So this glass slide can have very high affinity to the IgG. So after IgG attached, then we can put the analyte of the anti-IgG onto our solid support here that is modified, surface modified with the IgG. So the analyte, if the analyte composed of the anti-IgG, then they combine together like this, and with the gold particles, which was surface modified previously with the IgG, mix them again here in the system. So our gold nanoparticles can bind with the anti-IgG on top, and then they stay here on the surface of the glass slide. But if the analyte has no anti-IgG inside, then the gold, colloidal gold, cannot attach onto our IgG by itself because it's IgG and IgG, right? There are no affinity. So it's washed away. So we can use this kind of thing to see whether the color turned to red or not. If the color turned to red, that means there are anti-IgG on our analyte. Or we can also improve the detection limits because the red color of the gold is not very deep. So if we have very low concentration of anti-IgG, then small amount of the gold can be attached onto the surface, and we can hardly see the color of the red color of the gold. So what we can see, what we can do is enhance the color changing by adding of the silver ion. So silver ion can then reduce down very easily because of the reduction potential of the silver ion is about 0.8 positive. So it's very easily to be reduced and then attached on top of the gold. The silver reduced and then coated on the gold nanoparticles will change the color of red gold to be very dark black color of the silver. So this increasing the lower down the detection limit because we can notice the color changing easily with the black color of the silver. So how can we prepare the gold with the antigen on top of it? There are so many ways to do the surface modification of gold. One thing that we can do is instead of using citrate as a stabilizer, we're using PEI or polyethylene imine as a stabilizer instead. This is a polymer, right, with full of nitrogen atoms on the long chain polymer here. So if we use this as a stabilizer instead, so starting from a very simple citrate reduction method, after we have gold nanoparticles, we just mixed with the PEI, and then by dialysis, the citrate ion, which is very small, can be dialyzed out from our container, and then the dialysis bag, and our gold nanoparticle is now coated with the PEI. PEI with full of nitrogen atom, they can interact, or they can have kind of very reactive to some functionalities, and so with very active properties of nitrogen on PEI, we can then modify the surface of the gold easily. So the N, for example, can have a imine bond with the aldehyde group. So if our IgG have the aldehyde functionalities here, then we can have the attachment of IgG onto our gold nanoparticles. So at the end, we can like modify the surface of the gold nanoparticle with the antibody, for example, here. So this antibody-rich gold nanoparticles, we can use it to sense as a sensor to detect antigen. So with the gold nanoparticle full of antibody on top of the surface, if you have the antigen in our analyte, then the antigen can attach to the antibody on the surface of the gold. And because we have so many gold nanoparticles here, that means the antigen is now initiate the coagulation or precipitation of the uh, colloidal gold. They kind of aggregated themselves together. So with the increasing size of the nanoparticles, then we have scattering. The cluster of the gold nanoparticles here can scatter the light, and as a result, the color of the gold, colloidal gold solution changed from red to kind of purple or blue. So then we can use this as a sensor. What I show you here is we're starting from 50 ppm of the gold nanoparticles. So then actually the gold nanoparticle is not very expensive because we can use it in a very low concentration like 50 ppm like this for 50 microliter. Okay, and then we add 1 microliter of the sample. Okay, so in this case we developed this gold nanoparticles which is now attached with the antibody with PI and antibody. So we can use this to detect the leptospira interrogans. Um, so after 20 minutes of incubation with the leptospira interrogans, so as you can see in the picture over here, we varied the number of cells of leptospira interrogans in each epindof. So what you can see is that we're starting to see the precipitation of the colloidal gold at about 100 cells per ml of the analyte, right? So we're starting from the analyte containing 100 cells, right? But we added just only 1 microliter. So what we can see is just that amount of cells. We can see the precipitation of the colloidal gold in the epindof. So this is our detection limit for this kind of chemistry. There are many other detection methods for the colloidal gold. This is another example published in 2012. Right? In this study, they use this kind of things. Right? They're composed of 3 units. The top one is the antibody binding proteins, and then we have thioredoxin in the center, and then we have the gold binding proteins at the very end here is peptide specifically bind with the gold. So after that, they put gold ion inside and synthesis of the gold nanoparticle here. So gold nanoparticle synthesis in this chamber attached with the gold binding protein over here. So at the end, we have gold nanoparticles decorated with the antibody binding proteins. So these antibody binding proteins can then catch the antibody on top of it. So after we have these gold nanoparticles mixed with the antibody, then our gold nanoparticle is decorated again with the antibody on the very top of the surface. So if our analyte contain antigens, then we can have the antigen-antibody interactions, and at the end, our gold nanoparticles aggregated by these antigen-antibody interactions, and we can observe the color changing of the colloidal gold nanoparticle from red to something else, like this. So this using one-pot synthesis, right? Instead of synthesis of gold nanoparticles, using chemical reduction and then surface modified afterwards. So we can do it in just one pot synthesis, step by step, adding the first component with second component with third component and so on. So as you can see, again, the antigen can initiate the aggregation of the gold nanoparticles. So what you can see is the colloidal gold solution red color is now precipitated out as a red solid, okay, leaving the solution as colorless clear thing on. Another method for detection with gold nanoparticle is using click chemistry. The click chemistry is a kind of chemical reaction with the very high speed of the kinetics with a very fast reaction rate. So we use this kind of chemistry to like modify the gold nanoparticles on top of something. So in this case, right, we're starting from a sample holder. If the sample holders contain the antigen, then they can interact with the antibody. But now instead of put the antibody with the gold, they put the antibody here with a long chain polymer. So with the long chain polymer ended with kind of alkene ring here, right, which is very steric and rigid alkene ring. So this alkene can have or can undergo click reactions with the A side N3 here. So if we have the gold nanoparticle modified with N3, right, mixed with it. So starting from the antigen on our sample holder, so antibody attached on top of the antigen, and then we mix the gold nanoparticles with A side on top. The A side can then react with the alkene, and at the end, gold nanoparticle is now catched or stick onto our sample holders, right? So with a very long polymeric chain here, we can attach more than one gold nanoparticles on the surface, right? So this can enhance the detections of the gold by our naked eyes. So as you can see over here, with time passing 2 minutes, 30 minutes, 1 hour, and 24 hours, we can see that the color changing is then increasing, right, from slightly bluish color appeared at 2 minutes, but if we leave the chemical reactions to go further for 30 minutes or 1 hour, we can see the color changing clearer and clearer, depending on the time. So even though we use click chemistry, but it takes still sometimes to develop the color, because yeah, it's just very small amount of the cluster to attach with the our testing system. Another very interesting detection method is the direct imaging. For example, if our gold or metal nanoparticle uh, can be surface modified with the fluorescent tag and also with the binding ligand, which is specifically bound with a phospholipid of some kind of organisms, virus or bacteria. So preparing this nanoparticle system and mix with the bacteria or virus, then our metal nanoparticle can then aggregate it on the surface of the cells, right? So for example, in picture A and B, as you can see, there are nanoparticles aggregated on the surface of this kind of cells. And because we also attached the fluorescent dyes on top of the nanoparticles, right? So we can also detect it with the dark field microscopic image as well. So the nanoparticles, right, emit the fluorescent light because we have fluorescent dye on top of it. So now we can direct image the nanoparticles on the cells as the detection tools. So apart from antigen antibody system or the attachment of the nanoparticles on the um, lipid bilayer cell membrane, we can also use DNA as a as a target for detection as well. And there are many mechanisms can be used here. For example, we're using gold nanoparticles with the kind of DNA strand, right? Single-stranded DNA, which is complementary binded with the kind of DNA of virus or bacteria that we want to detect. Then this can induce the aggregation of the gold nanoparticles, and hence the color of the gold nanoparticles is shifted. We can also use PNA, synthesized PNA instead of DNA to increase the affinity of the binding. And there are many more. Uh, it's quite a very um, fancy way to design the detection mode using the DNA complementary base pairing system, thing like that. The first example that I want to show you here is that we have the DNA of the virus that we want to detect, or maybe RNA of the virus that we want to detect. So we designed the gold nanoparticles, two kind of gold nanoparticles. The first kind blue color with the complementary base pairing DNA here, one single-stranded, designing to pair up with half of the target DNA. Another half of the target DNA using the red color labeled here is specifically bind with gold nanoparticles with another series of single-stranded with will bound complementary with the complementary base like that. So blue color bound to the first half, the red color bound to the second half. Then if we have the target DNA here, the blue color and the red color gold nanoparticles can then aggregate it together. So as a result, the color is changed from red to blue, for example. And we can double check it by the temperature as well, because there are temperature for detached the DNA stranded out of each other, because it's just the hydrogen bonding, right? So with increasing temperature, the DNA double-stranded helix can be broken down into single-stranded helix. So playing with temperature, we can double check whether this is the false detection or not as well. Another thing is that we're starting from two sides of the gold nanoparticles again, which can bind with the linker DNA strand. This is from the virus or from the DNA from the bacteria. So if we mix these various sides of gold together, so binding with this linking DNA stranded, then we can have the aggregation. So obviously the color is changed, and now we can also detect it by the TEM image. As you can see, the bigger gold nanoparticle is now aggregated together with the smaller gold nanoparticles by this kind of mechanism, and so we can see it directly from the TEM image. So as a result, the color is changed, as I mentioned earlier. Not only the double helix, the DNA can form the triple helix as well, but with the triplex binder. So this is a kind of chemicals that induce the formation of the triplex. So as you can see here, the red color DNA coding here is the target DNA. So we have to design the gold nanoparticles together with the probe DNA here. So with the gold nanoparticle together with the probe DNA on the surface modification, it can then bound with the target DNA using triplex binder. So as a result, the gold nanoparticles aggregated, right? So with the cluster of these gold nanoparticles, the scattering of light can be seen in blue color. So we can use this triplex binder as a kind of tools for DNA detection as well. DNA can also incorporate with the polymer chemistry for enhance the detection as well. For example, we have two things here, two samples here. On the left hand is a single-stranded probe. On the right hand is the probe with the target, right, bounded together as a double-stranded helix. And then we add our gold nanoparticles inside. So after we mix the gold nanoparticles inside, we have just kind of mixture. And after that, we put the conjugated polymer inside. The conjugated polymer is the polymer that can have affinity with the probe DNA. So if the conjugated polymer interact with the probe DNA, so the probe DNA is instead of being as a stabilizer preventing the gold nanoparticle from aggregation, the probe DNA is now removed from the gold surface by the conjugated polymer. So the gold can then aggregate it afterwards. So we can see the color changing of the gold colloidal solution from red to blue. But if we starting from probe and target duplex already in the very first step, right? With gold nanoparticles, they stabilize, but conjugated polymers cannot remove the probe from the gold nanoparticles. So as a result, our gold nanoparticle is still stabilized by the DNA system. So the color is still red, for example. So we can use the polymer and go together for detection. So as you can see, there are many designs to use the gold nanoparticle and as a colorimetric detection of DNA and everything. And also, antigen antibody, we can have strip test. DNA can also perform a strip test as well. So the design is quite similar, right? So from the conjugated part, we put RNA target sequence here from the patient, and then we have gold nanoparticles probe here as well. So by the chromatography, everything flows to the right hand. Right? Normally the membrane using here is the nitrocellulose. Okay, so our mixture move towards the right hand side, and we have the detection and the control. So at the detection, we have the DNA that is have affinity binding with the target, and the target also binding with the gold. So as we can see that we have everything complex together here. But at the control zone, we have kind of the DNA that can interact with the DNA on the gold nanoparticles. So this is the control zone. So if we don't have the RNA targets from the patient, so the gold nanoparticles cannot complement binding with this blue color DNA at the detection zone. So only the right hand lines can be seen as red color, but on the left hand is not. We can see the color from the control zone only, not the detection zone. And as again, because gold nanoparticles is in red color, it may not be very deep color enough to see by the naked eye. We can also enhance the color by adding silver ion, for example, into our system. So the silver ion will be reduced on top of the gold and changed color to be deep black color. Right? So we can increase the detection of the naked eye using silver ion as well. Not only the strip test, we can also develop kind of smartphone for on-site sampling as well. So this is a project done in Rwanda for detection of HIV and syphilis. So the method of detection is very simple comparing with the previous system, because this is just antigen antibody mechanism as well. But instead of using strip test, right, we have smartphone. So the smartphone can take a picture, and then from the color changing here, the smartphone can then convert kind of color to be numbers, and then we can use it to detect the HIV and syphilis in a very remote area, which is very far from the hospital, right? And the distance is very problematic over there. So we can use this smartphone, which is very portable, right, and use it for detection, things like that. So there are many kind of detection methods using DNA, using proteins, using so many kind of things. So just the design, right? And the nanoparticles can act as a reporter's unit, right, by color changing. So the very advantages of the gold nanoparticles, or any kind of metal nanoparticles, but normally we use gold, is because we can detect it by our naked eyes, right? So the detection is very simple, right? And because the gold nanoparticle is quite stable, so the shelf life of this kind of strip test is very long as well. So it's very useful and applicable. So these are just some of the kind of applications of gold nanoparticles on detection of diseases. Right? But actually there are many more, right? But I just want to give you the idea about this kind of applications of gold nanoparticles, and I hope you enjoy my talk today. Thank you very much, and thank you very much indeed. Goodbye.